A global supply chain generates over 1 million distinct data points every 24 hours. Cargo routing, energy consumption, material extraction, a continuous stream of operational telemetry. Yet, to measure the environmental impact of this machinery, we still rely on static spreadsheets and manual data entry. We take months to collect retroactive data, compile a life cycle assessment, and file a report on events that have already happened. That methodology breaks the moment it encounters Scope 3 emissions. You cannot manually track the dynamic carbon output of every third-party supplier, vendor, and downstream user in an interconnected global economy. The required volume of calculation demands a structural pivot. We have to move away from static, retroactive reporting and adopt systems capable of real-time environmental decision intelligence. Retroactive environmental accounting cannot keep pace with these data volumes. Navigating modern regulatory requirements requires a transition to a predictive, AI-assisted architecture. To build that capability, we need a new blueprint. We have to construct a next-generation, AI-native LCA pipeline from the ground up. The first requirement of this architecture is speed. We will replace the manual analysis bottlenecks with predictive machine learning models. The second requirement is completeness. We will automate the imputation of missing lifecycle inventory data so assessments aren't derailed by gaps in the supply chain record. The third requirement is translation. We will deploy strictly governed generative AI to produce the final documentation, locking the outputs to ISO 1440 standards. And sitting above all of this is the ultimate constraint: transparency. Every prediction, calculation, and estimation in this pipeline must be mathematically defensible to a third-party regulatory auditor. You cannot execute precise environmental science at scale without first mastering your data infrastructure. The immediate problem in any real-world assessment is that raw operational data is always incomplete. A supplier doesn't report their exact water usage, or a transit manifest drops the fuel efficiency metrics. When manual analysts hit these gaps, they either halt the entire assessment to hunt down the missing number, or they plug in a highly inaccurate generic average just to finish the math. We can solve this computationally using machine learning clustering and feature engineering to impute those missing lifecycle inventory values. It starts with your isolated silos, raw operational data, and massive LCI databases like EcoInvent. We construct a feature intelligence layer directly between them. Here, clustering algorithms identify hidden patterns, grouping scattered historical data points into specific material and process families. When your operational data comes up short, the algorithm doesn't guess. It analyzes the known variables of your specific material, finds its mathematical proximity to established clusters, and dynamically fills the void with high probability values. Machine learning removes the human guesswork, turning missing information from a project-ending roadblock into a computable, predictable variable. With our operational data now fully complete and perfectly structured, we move directly into the predictive phase of the architecture. This is where we move from simply counting the carbon of things we've already built to predicting the impact of things we haven't even manufactured yet. To do that, we introduce a model optimization system. This replaces standard linear equations with a multi-layered neural network matrix. Inside this matrix, regression models process the massive volume of newly imputed lifecycle inventory data points we just generated. Simultaneously, time series models ingest live, real-world operational inputs, streaming directly from the supply chain. Ensemble models then combine both of these inputs, the historical inventory baseline and the live operational telemetry, to calculate a final predicted emissions output. Because this calculation happens in seconds, engineers can simulate dozens of alternative materials, different vendor suppliers, and complex routing options before physical manufacturing ever begins. This predictive modeling integrates the LCA directly into the design process, allowing engineers to adjust environmental outcomes before a product ever reaches the factory floor. But there is a strict friction point in this industry. An AI model is entirely useless if regulatory bodies cannot audit its logic. To achieve compliance, we must quantify the exact mathematical uncertainty of every prediction the system makes. We do this by running Monte Carlo simulations. This is the gold standard for sensitivity analysis, generating thousands of distinct probability distributions to show the absolute high and low bounds of our carbon output. Even with those bounds established, we face the problem of data drift. Real-world operational conditions eventually change, and those silent shifts slowly invalidate the accuracy of the original model over time. We counter data drift by building MLOps directly into the architecture. We place diagnostic sensors across the predictive layer. If a live data feed shifts out of expected bounds, the system triggers a quality alert and immediately routes the anomaly into a retraining pathway. This automated alert and retraining cycle ensures the system maintains its service-level agreements continuously without requiring human intervention. Without MLOps and Monte Carlo validation, AI remains a massive compliance liability. With them, it generates strictly investor-grade evidence. The final layer of this architecture ensures that this mathematically validated data is actually usable for human stakeholders. You cannot simply plug raw supply chain data into a commercial, open-ended large language model. Doing so introduces unacceptable hallucination risks into a regulated environment. Instead, we restrict the large language model. We architect it so it can only act upon the deterministic, validated numbers coming out of our MLOps pipeline. The LLM is explicitly instructed to structure its output according to strict formats, dropping the data securely into rigid ISO 14040 and GHD protocol templates. Simultaneously, this cleanly structured data is pushed via API directly to visual dashboards. ESG researchers and process engineers can look at this presentation layer and get instant, highly specific answers to complex queries without parsing raw code. By governing the GenAI precisely, it acts as the perfect translation layer, bridging the deep mathematical modeling of the backend with the corporate policy requirements of the boardroom. Look at the complete architecture. We have a continuous automated flow, raw data ingestion into the ML predictive layer, validated by MLOps and Monte Carlo simulations, and translated by GenAI into a finalized dashboard. Combining ML for inventory prediction, MLOps for auditability, and LLMs for reporting rewrites the mechanics of environmental analysis. We have successfully transitioned from manual environmental accounting to automated environmental decision intelligence. A product engineer can now load a new design and perform an instant hotspot analysis on a Tuesday afternoon, rather than requesting a manual LCA report and waiting 6 months for the results. While the system operates with significant computational speed, its primary utility is the verifiable, audit-proof scientific rigor it brings to every assessment. For sustainability professionals, deploying this technology translates directly to career impact. Mastering these AI workflows elevates ESG analysts from backward-looking compliance reporters into direct influencers of corporate strategy, capital allocation, and resilient infrastructure planning. Mastering these workflows allows professionals to embed sustainability directly into the technical frameworks